Hello，今天是7月27号啊。从上次直播到现在，哎，我的家 never be the same。You see there，这地方，那前几天在20号那天，还是古尔邦节，还是我26岁最后一天，家里他妈居然发了大水了，那混蛋！10楼就调查之后，我发现就是10楼的那家他妈的阳台上水这个积水了。他那个地方后面该排水的他没有给它弄，他没有给它清干净，导致他阳台积水，完一下就被灌满了这么高，顺着烟道直接灌我们家了，灌到烟道里面直接灌我们家了，可糟了哉了！我们家所以说整个家里面是飘在这地板整个是飘在水上的。现在今天这石灰刚到，我们21号买的，1个星期才发到郑州。这石灰刚到，我们昨天都上了1节课，但实在没心情。哎，行吧，现在开始啊，开始，接着削。这是第一个苏联人的课啊，没事的。发生什么事了？邪了门了。发生什么事了？我操！没有。那怎么但闻人语响？哎呀，这破逼网速还不行，我操了！
Which consists of 2 parts, rock mechanics and slopes. My name is this is my name, and I will be doing rock mechanics. And Adam will be doing slopes. But
他妈的还课不是跟我学的还一样吗？学没开那个。
please, if you have any organizational questions, like enrollment, disenrollment, and so on, so please, admin, please send to this email, not to us. To us only the questions regarding the material. Okay?
说什么东西我靠！So,
the unit will be organized the following way. Rock mechanics takes 2/3 of the unit, exactly 8 weeks out of 12. And slopes, one circle. We have 3 lectures per week and 2 tutorials per week. Tutorials will be face-to-face and online, but it might happen. Okay, all the tutorials start next week. It might happen though, with rock mechanics tutorials, at least the first few will be online only, because of the tutors is timing. He might be requested to stay 2 weeks in currency.
你妈这什么狗屁玩意！我操！这他妈怎么学？我操！我他妈惊呆了。
Then the first students will be online.
我他妈的服了，半天都不出声呢。哎，我他妈操了我！这直接没声了，我操！你们什么狗屁玩意儿？这他妈网课怎么上？他妈什么垃圾网课！我靠了！
For consultations, I will post on LMS time. It will be online, and if someone needs face-to-face discussion, again, discussion with respect to the material, please send me, okay? Now, there will be 5 lab sessions, plus 1 repeat lab. So, you have to take 5 labs. But, and that's it. If you miss something, then there will be repeat session. For the lab, sorry, but you have to do safety induction. That is the strict requirement of this university, that without safety induction, no access to equipment whatsoever. Okay? So you have to do it online, you have to print your completion certificate and bring it to your laboratory. If not, sorry, you will not be allowed to do that. Okay? There will be online labs for those who cannot come to this country. Well, we will send the material, we will send some photos, movies. So it was just because of the pandemic. Unfortunately, well, it's not a good replacement. You all understand that nothing to do. So you are here, you go to the lab, the full exposure to the lab. Okay, this is safety induction online. This lecture, the slides are already uploaded to LMS. All slides will be uploaded, plus whatever I will be writing during the lectures in a notebook, in the digital notebook, will be uploaded. Okay?
Not okay.
That's it. Okay. In rock mechanics, there will be 2 assignments, but there will be 1 assignment, but it will have 2 parts. Such that we will be doing them over the period, the lectures, not immediately. So, both assignments, together have 20% of the work. 5 labs, and each lab you have to write a report. It's a group report. Well, previously we had group assignments and individual assignments. Assignment form the groups for the last 5 to 7 students. If, well, we still don't know the enrollment, so my group, where it is decided. But ideally, it should be constant. Ideally, start thinking about it and getting together, form the group, such that we can work together. And of course, because it is the group, then we'll discuss. Final exam 40% for application. For the slow part, assignment 50, and the slow part of the exam will be 50. And you submit assignments online, not usual, don't forget about the cover, just in case it goes to the assignment. Who knows? I have to tomorrow with the English. And report, put it report. Well, it's long. This whole thing is about research. Academic conduct.
我他妈服了，这他妈的，唉，我要把 VPN 关了，操你妈
！Well, then I'll just want to listen to what contribution no always. Don't change anything. Yeah.
能不能给我去鸡巴牙？操你妈！
So, about slopes, Adam will tell you.
What is this?
In Orthodox, essentially, the lecture notes are sufficient. They will not ask you anything which is not in the lecture. Okay? That is sufficient. You need textbooks if you need. To look at something deeper or if you feel that you don't understand something. Okay, recommended textbooks. Brick and Brown. This is the sort of classical book.
What?
It's beginnings from around MINE. It has a lot of other.
你这让我怎么看？我他妈怎么学？我他妈！我学你妈了个逼！我，你这他妈的垃圾网课！我操，网他妈还不行。
Some engineering applications on Hudson and on Subinyaski. These are all old books. The new books you have. Tutorial files on numerical methods and that's it. I would say that the old books already is my patient. No, okay. That is about the organization.
你给我滚吧你！我操你妈什么狗屁玩意儿！我操！
Well, this is 0.07, so that should give you that total resistance, which will be less than the small. Once you get that, and you've got the volume, then you can work out what the pressure is. Once you've got the pressure across each of them, you get the same, you can be working backwards and get the volume to each. And when you add the ground, it should be 120. But we'll cover it again on Friday, sorry, right? Things you've done. Okay, any questions, just email me or...
Excuse me, who are you?
Yeah, it's in there. Sorry, man. The videos are so good. No.
搞的什么东西？我操了！
And then you, after that, you will start. Okay. So, can we start? Okay, let's begin our lecture. So yesterday we discussed traditional applications, nothing specific, and all of these applications you probably know already. Now I will continue our introduction. Now I will just go through what we call novel applications. And then after that we will start the actual part of the video. So, in situ leaching, this is how novel it started at the second part of the last century, but it's still not very much used, only for uranium. Underground storage, extraction of geothermal energy, deep sea mining program, and even extraterrestrial mining for construction. Even extraterrestrial mining, of course, is not started, but it's real. There is no doubt. And definitely in your life, one needs to be prepared. Uranium in situ leaching. What is this? So the idea is very simple. So you have the ore body, you you pump in leaching solution, you let it to dissolve the ore, and then you pump it out, and then you treat it to extract the actual material, the actual mineral. Well, it's very attractive. You don't need to mine, you don't need to send people there. But of course, the productivity is very low. There was a project in the US doing city leaching of copper. It was not economically viable. The traditional method is better. The only place where the ECT leaching is used is uranium. Why? You cannot send people there. It's radioactive. Then no matter how slow, it delivers without damage to the personnel. Okay? That is why. Well, there are a number of in-situ leaching sites. There is a list. Well, it's not used here as far as I know. It is used in the USA as well as in Europe. The second big area of application is the radioactive waste storage.
Storage.
It's the spent nuclear fuel. In the USA, some locations were selected, but one of them is Yucca Mountain. It's here.
Spent nuclear fuel.
This is the site. So this is how it looks like. This is the storage. Here you have the containers with the radioactive waste. You need a layer of unsaturated rocks in between the storage and the saturated rocks in order to prevent the radioactive waste or contamination of the water. So this is how it is done. Site viability assessment includes the presence of groundwater flow and the site viability assessment includes the presence of groundwater flow and the stability.
The transport молока.
The assessment includes the presence of groundwater flow and the stability system. Contamination. So it means that you need to see what water is in what is called unsaturated zone, in this case, or insaturated zone as well. Geological activities, you don't store it for a year or two. Store the radioactive waste quite some time, and therefore geological activities in the region do matter. If there is an earthquake, then earthquake can happen, then the storage might be destroyed. And contaminated, we don't want that. Volcanic hazards, and unfortunately, a new part. You see, geological effect of chemical seismic hazards, they would apply for everybody. Right? If there is such a possibility, they can destroy the mine. But what is not known in the mines is this thermal effects. Radioactive storage, radioactive material, waste material, heats itself, right, this time. So it increases the temperature, then the temperature of the rock gets increased, it creates thermal stresses. Not very big thermal stresses, unfortunately. The materials even are under low stresses can break, but not in this time. It's called delayed fracture. You know that now some medieval buildings get collapsed because the material is exhausted, its ability to withstand the load over a very long time. The same can happen to rocks. At least this sort of possibility have to be taken into account. Radioactive waste would require thousands of years to become safe. In thousands.
兄弟们，你们看完教教我，那怎么辨别他的口音？还是说他这个口音的确是普通人难以辨别的？
Thermal stresses can do local damage. That needs to be taken into account. This is, and honestly, mining actually not entirely very active mining is 200 years. So we don't know what will happen in 1,000 years. We have no experience on that, no knowledge, nothing. So storage of radioactive waste for thousands of years may not be a realistic scenario because we cannot predict what happens.
Radionuclide.
So when we approach geological times, anything can happen. So the only viable option for us is to have, and we need to call it temporary storage, to wait for a better technology to process the waste, to make it safe. But you cannot expect to put it in the ground and be safe forever. Nothing happens, nothing survives forever. Okay? The seriousness of the issue was long ago recognized in Canada. They create the called underground research laboratory. It is mining. It's the only purpose to create a research excavation.
Research.
To do research.
And do research.
So they have 113 meter deep shaft and experimental excavation here. So this is how it looks like.
Experience room. 说吉尔，我操
All the measured stresses, they look at breakouts. This is the breakout. So this is what we call spallation. You see, the
What
profit chips off. This is happened. This is due to acting stresses there. And if the same mechanism would happen at a larger scale to the rock, so this is more or less benign. The rock burst fracture. So these are the observed fractures. And you see the shape. The next application is called strategic petroleum reserve. Well, the whole story started long ago when the first petrol crisis happened. The price for oil jumped up because of the Mid-Eastern, because of the control of the other countries. And as a result, the price of petrol jumped a lot, and Americans decided that they need strategic reserves to keep oil, to buy oil relatively cheap and keep it there. So how to keep? Where? So they use salt or body. So they make caverns in salt by dissolving salt. This is sort of in situ leaching, but sort of easy way. So they put water in, pump out the solution, the brine, and then put in petrol. The advantage of the salt is that salt is not permeable. So you don't need to create storage tanks. It's up into the cover, and then when you get the oil out, of course you have to clean. That is a common occurrence. Oil, the cleaning process, very good. Okay, one cavern is not enough, so there is a group of caverns. So this is the map of strategic petroleum reserve locations in the USA. The next one, hot dry rock. Hot dry rock is a technology to use temperature underground to produce electricity. One of the methods is so-called hot dry rock. And it is based on the notion that if you look at this map, okay, the color scheme is degrees per kilometer. For instance, this one. See? There are places where each kilometer the temperature increases by 70 degrees. The rock is quite hot. Of course, why the rock is hot? Because it is hot down there, plus there could be local radioactive material which hits the rock. So this is the idea. So you drill for three boreholes. This is the central boreholes, and you pump in cold water. Just water. It goes to the hot rock and gets hot. So usually it is about 200 degrees, but it does not boil because the pressure is high. Right? The higher the pressure, the higher the boiling point. And then you pump out the hot water, and when it is pumped out on the surface, the pressure drops to the atmospheric pressure, and it produces very hot steam. And then you drive a turbine and produce it. Okay. This plants were built in the USA, in Europe, they do work. It's not cheap to do it because we are talking about 10-ton depths. We need to have porous rock because this water has to reach the outlets, the bottles from which it outlet out. But all of it puts certain demands on the determination of the location of the place.
Location.
Okay, there are locations in a
Determination.
to be done, and it is that people work on it. So this is, for instance, you can use for permeability, you can use fractured reservoir, or you can make hydraulic fracture.
Fractured.
There is a problem. So, why the hot dry rock is not yet a mainstream renewable source of energy is because you should remember, a rock has very low thermal conductivity. If this part of the rock is very hot, if you pump in cold water and get hot water out, you will cool it down. To get the heat from the adjacent rock, it will take very long time. So after a while, the whole thing stops working, and you have to drill boreholes in a new place and start it all over again. This is the main impediment to this quite interesting activity. Yes, yet underground the geothermal conditions are used. In this city, there are a few pools which get warmed by water from underground, hot water from underground. So it is used, but it cannot be used at the industry scale because it is so far. Maybe you will find a way out of this problem. These well applications are relatively new and in development or in use. There are more esoteric applications. One of them, deep sea mining. Okay, there are a lot of minerals under sea bed. We don't use them. We know that the minerals accessible to us can get eventually exhausted. So there is a lot under oceans that we need to learn how to do it. The depths are big, you cannot bring people there. There is a limit.
Ballast.
So it's only a robot or something like that. So you have a machine which would crush the rock under the seabed and then try to get it out. Well, I cannot say that it is easy, I cannot say that it is the best solution, but at least people start thinking about it, and again, maybe it will be up to you. To do oneS2. Well, CSIR had a project which considered a number of places with minerals. For instance, these are the places, this is the place in the ocean where you have gold, silver, copper, and zinc. So there is something to mine, just we need to find the proper technology. Deepwater petroleum, not yet used, but eventually petroleum reserves are exhausted. Proper technology. water petroleum,
Deep water petroleum, deep water petroleum，这他妈谁他妈能听懂 deep water petroleum？
not yet used, but eventually when petroleum reserves are exhausted, we have to go to deep water.
Deep water.
But again, it is a new technology which is actually to develop. And the last one, extraterrestrial mining and construction. We're not yet there, but we can think about it. So out of all planets, we are of course talking about these ones, the giants, who are accessible to us. And it is not even clear if they have much of the resources that they're made of gas. So it is for extracting high value minerals or the processing and manufacturing in situ. That is a good thing because you can use any dangerous technology. If it is moved, there is no environment to actually protect. Or you can use it for local usage. But there is so-called helium-3, an element which is not, which does not exist on Earth, but does exist on other planets due to on the moon, for instance, due to solar radiation, and it can be used for nuclear power. The most attractive of small planets like asteroids, because it's easy to land, easy to take off. It's very difficult to do anything there. How would you drill and cut in low gravity? All our drilling and cutting excavating equipment is heavy equipment, which means it relies on the gravity, right? So imagine you have an excavator, you try to you touch the ground with the excavator goes up. No gravity. Or microgravity, as we say. So these are the challenges. Okay, this slide shows what sort of material you can get on the moon. Gravity on the moon is probably sufficient for heavy equipment, but how would you deliver that heavy equipment? It would require new technologies. Maybe up to you to develop it. Okay, this is the list of the elements. Now people try to develop some underground mining technologies. Again, the vacuum, if you want people to operate the
ceiling,
provide air. Okay. So, we come to the end of the introduction. So what is required to design in rock engineering? First of all, you need to know rock and rock mass properties. Second, the original in situ strength. Then you need to know stress concentration produced by the excavations. Because to make an excavation is an empty space. So you transfer the load to the walls. You overstress the walls. There will be a chapter on the ground excavations where we will discuss what sort of stress concentrations can happen. So, stress concentration. And the last but not least, we need to understand the manufacturing process. If in materials engineering, everything is relatively simple, what many things are broken by tension or by shear. And the stress state can be decomposed into this simple stress base. underground, you have mainly compressive stress. There are different types of failure can happen, and we need to understand how it works. So this is understanding of fracture process. Unfortunately, these two parts are challenging as well. Rock and rock mass properties. How would you know them? So rock properties, okay, you get rock samples from the course and go to the lab and test. Or do it in situ using express methods. How many samples you can test? And the so-called rock variability. The same rock taken from two different places have very different properties. How would you deal with that? It's rock properties, so about mass properties. It's a larger scale. There is so-called scale effect. And again, in the chapter after the next, in chapter 3, we'll discuss the scale effect and so on. So there are challenges with that. So to say it simply, we have not created the rock mass in the earth. God did it. God did not leave specifications for us. So we don't know what is it. And that is the fact of life. And we need to live with it. Original stress state. Original, which means before we started excavating. Because when we start excavating, we change. But before, we need at least to design excavation.
Before нет.
To know what stresses are there. There will be a chapter on stresses, and it is not easy because it is stresses the weight of overburden, particularly movement adds to the stresses, it adds a lot. And it's variable from one place to another and how to measure.
Measure.
As a calculator measure, it's difficult to calculate. It's much more difficult to measure. The method, there are many methods of measurements, we will go through them, but it's not a simple process. The only thing which is relatively simple is, of course, stress concentration produced by excavations. Well, it's infinite unit method. So what are the main objectives in our thinking? First, understanding from deformation is not as simple because we understand it quite well when it is elastic. Rock is not always elastic, especially if it is a micro. Then what happens there? How in our mind, how to avoid failures, that is the absolute goal, but at least predict them. Because if we don't, and it happens, it can change. Controllable rock fracture techniques mean, in many cases, since we have to fracture, is to do excavation. But can we use natural fracture or natural failure to take it under control and to develop these techniques? Blockade is an example, by the way. Controlling rock properties can be improved rock properties, in some cases, yes, using grout, for instance. Stress and displacement measurements, look at existing techniques for that, and developing efficient rock pricing. Well, rock failure is a major trouble. We have a number of them. It's slow slide and failure and disability. Considered in the second part of the unit. Failures in underground excavations we will discuss. Borehole breakouts will be discussed. Mining-induced seismicity we will not cover it more in this unit. And earthquake induced by the production. Surface subsidence we will not cover here. Also, and this is also to do with support mechanics, alteration of water regime due to excavations. And this can create a lot of environmental damage and social damage, for instance. People use agriculture industry started mining water, disappeared. You change the water industry. And agriculture in this place is no longer possible. So you will have to face lawsuits about that big social movement against. So these are the things which need to be taken into account, and this is the role of mechanics to do. Then foundation failure will not function. So talking about failure, we need to consider failure under different types of impact. Opposite is stability. This is what we want. Stability of excavation under different types of impact. There's mechanical, gravity, there's water pressure, metallic impact. So terrestrial mining. Physical temperature, for instance, the radioactive waste storage, and chemical impact. That is a very important part which sets aside the whole of mechanics from other branches. We have a number of scales involved, and the properties are different in different scales, but testing is only possible to source. Typical rock sample size, 150 length, 80 in maximum. Diameter, if they are taken from the cores, they can be smaller. A lot of samples, 5 millimeters in diameter. It has nothing to do with the scale of excavation, but the diameter of excavation can be 3 meters, and the length 100. So you see, we are checking a dust segment as compared to what we need. But we don't have machines which can test bigger samples. Because the machines are operating force. And force is the stress to the system. So you stress times square of the section, times the cross-section, area of cross-section. So you increase the sample 2 times on sides, and the force should be increased force. Because I will show you some results. The biggest I know is 2 meters. It's a huge machine. That is, we cannot do completely. Not well. Unpredictability for properties and variability, so proper variability. We need a lot of samples to make proper prediction. What can be done? What is done? Is monitoring. People keep measuring. Mainly they do microscopic imaging because it can be done from the distance. It's not in the way. So it's not. It is not sufficient. What we need to do is to measure the spacing of the surface of the excavation and how to do it during mining operations. It's another question. Okay, this is the plan. The first part of the games is the plan for the second part of the So we'll start with overview of mining methods. We will do it today. Then we'll chapter 3, laboratory and site rock properties. Chapter 4 is stress strain and elasticity. We studied that from I think year 2. The practice shows that nobody remembers that. And because in rock mechanics, the conditions in rock mechanics is that there is rock mass everywhere and complex stress strain. So you need to understand the stress and strain in full. It is as they teach it in proper courses of mechanics. And elasticity is the simplest case of stress strain behavior. We will discuss that. Stresses and rocks and in situ stress. There will be some scale effect. Then deformation. Then mechanism for fracturing. It is a long chapter from the different situations which can happen. The stability of underground excavation of rock mass and some introduction to the mechanics of rock excavation. So this is what we are going to do. Well, Wolfgang Germanovic contributed to this, to development of this field, and that finishes the introduction. I think you have a break now. Now tell me, how would you prefer? Have a normal break or have a shorter break between the clouds? So 5 minute break, right? Good. What's my look methods? Okay, let's continue. Okay, this second chapter, on the ground minus methods, is just a revision. It's a short overview of the existing minus methods. I'm pretty sure you know this better than me. So, what are our learning objectives? Classification of minus methods, basic minus methods within the classification, and basic principle of selections of the minus methods. Okay, this is a typical picture of underground mining in this heating body. Okay, we have the main shaft, then the excavations in different levels.
数据。哎呦，我他妈的，我他妈要晕倒了！我这苏联教授这什么口音？我靠，这怎么那么的过来？他说英文的，我操，谁居然能听懂？我操了！
So you can see, for instance, here you drill for the quartz, and here you excavate. So this is an ideal picture of the excavation.
Schematic.
我他妈的惊呆了。Spread. Asleep. Pump station. Steel. Farm. Shop. 通风井。1.5 度，1.5瓦，豆。豆。Savez-vous au badi. Amiwali. 还他妈的气人啊！再到。放旷幽情，啥这个意思？放长，easy，很好。Exploration brief。
Excavate. So this is an ideal feature of the excavation. So there are three types of mining methods. The mining methods, of course, are distinguished by the order with which you excavate and get the ore out, and by the way you support the excavation. So the first one is about naturally support excavations. This is a mining method based on natural support, which seeks to control the rock mass displacement through the zone of influence of mining while mining proceeds. This implies maintenance of the local stability of the rock around individual excavations with more general control of displacement in the near field domain.
他妈的，读课文，我操了！
Of displacement in the
我最鸡巴烦读课文了。This implies maintenance of local stability of rock. Local stability of rock. Maintains local stability of the rock rather than individual acceleration and more general control of displacement near field domain.
near field domain.
Done.
In the natural supported mining method, the most common is
Connecting drift. Pinch. Lag. Wouldn't be lag.
rock and pillar mining. So you all know that you leave pillars of the opposite in place to support the rock. The negative. So the positive of this method, you don't need to direct any support. The negative is if you leave the ore there. Well, it is used in coal industry as well as gold, but the terminology is different, both and pillar mining. So this is how it happens. This is, for instance, a pillar.
我他妈的真的要晕倒了，我实在是难懂，我根本不知道他在说什么。发生什么事了？马老师，发生什么事？哎呀，这个叫什么？阿卡迪还叫什么？说马老师，发生什么事了？哎，想的服了。
So you have an excavation, you drill blast holes, you blast them, and then the debris are used to support the walls of the excavation from convergence. Well, you use this method when the core strength is moderate to strong. Wall
鸡巴东西，我！你最开始是从哪儿踩，他妈到哪儿埋？
of the excavation from convergence. Well, you use this method when the core strength is moderate to strong, but not strong whole stroke.
Accommodate.
Deposit shape can be irregular and discontinuous. Deeply steeping deposit. And when the end rate is fairly high. Further development cost, high mining cost. However, due to backfill operations, we use the host rock, the debris of host rock to backfill the excavations. Labor intensive. Host rock rock, the debris of host rock to backfill the excavations. Labor intensive. Shrinkage stepping, and again it is based on the backfill. You blast the rock, you leave it in the spoke, and then from beneath, from the drop of it, you get your extract. Conditions of in the spoke, favorable. Shrinkage stopping, and again it is based on the back field. So you blast the rock, you leave it in the spoke, and then from beneath, from the drop of it, you get your extract. Conditions of use: coastal and strong. Well, there are other characteristics because you leave the ore in the excavation broken pot, then it should not oxidize or spontaneously combust. Otherwise, phosphorus should be quite strong. The deposit shape should be tabular or lenticular with defined boundaries. Otherwise, it's not convenient to do this method. Steeply dipping from 1 to 30 meters wide. Large extent and very high overhead. It is suited for smaller scale operations, moderately well production, labor intensive and dangerous work conditions. But more critical investment, moderately selective, you can select bypass the parts with low overhead. majority of the oil is tied up in this salty extracted fully and open to be subjected to oxidation, taken from combustion. The last class is unsupported. You don't support any installation. This is long-ball annotating mining methods.
我受不了了，我要困死了，我要去睡觉去了，起来再说吧。